Switching gears now, one of the big things missing from the LMS is how do we handle user authentication to determine if somebody has typed in the right password when they try to log into their user account. So anything that does authentication, such as a web server, where a user types in their name and password, has to have some way of verifying that the password they typed matches the password on file that they chose at account creation time. In theory, this is trivial. You just store all the usernames somewhere and store all the passwords somewhere. So here's just some very pseudo C# code. Name typed is the username they typed in to the web browser on this login attempt, and pwd typed is the password they typed in. So we have some data structure called users. We just check if users contains that username. If not, it's an unknown user. If it does contain that username, then we verify that the password they typed matches the password for that user. So we have some dictionary mapping usernames to passwords. And if whatever they typed on this login attempt doesn't match the one on file, then we reject the login. So this is all pseudocode though, so where do we actually store usernames and passwords? And there are considerations, important considerations, because passwords are so security sensitive. So this is why we've kind of left it off until now. The first thing to try is, well, let's just store usernames and passwords right in the database. So maybe we make a new table user info that has usernames and passwords. So this is like the library Joe and Ben and Dan and so forth. And these passwords here on this slide are actually 4 of the most commonly used passwords in the world, which using a common password is bad, but we'll talk about that later. For now, let's just say, okay, it's fine. Let's save these plain text passwords straight in the database. So in SQL, what you would do to verify that a user has logged in correctly is take the username they typed in, take the password they typed in, and then just do a select out of that table where the username is this and the password is that. And that will either return 0 or 1 rows. If it returns 0, then the username and or password didn't match anything. Otherwise, you get the 1 row. And so all you really need is, if the result, so this is like a link query, if the result does not contain 1 row, then it was an invalid login attempt. Okay, so storing passwords in plain text, hopefully that's raising some alarms for you, and it should. But why? So let's think about why this is a problem. Users of the database, or users of the LMS, the web server, they don't have direct access to the database. So remember, we talked about how there's your Canvas password, and then Canvas has its own database password. Your Canvas password is not actually giving you direct access of the database. So only the people who should have access to this user info table, in theory, they are the only ones who have access to it. So in a perfect world, there's nothing wrong with this. We could actually store usernames and passwords just like this in plain text. But obviously, it's not a perfect world. We've talked about at least one way in which people who are not supposed to have access to a database can gain access to a database. So we've talked about injection attacks. Through an injection attack, you can make yourself an administrative account on the database sometimes, and then you could go and examine any table you want, or you could just run a select command and get all the usernames and passwords potentially. Turns out injection attacks, at least nowadays, are not even the most common form, or the most common way of stealing information out of a database. Social engineering and physical breach. So let's talk about a physical breach first. That's just, somebody gains physical access to a computer that they shouldn't have access to. Imagine you go on a tour of some facility. Maybe you get a tour of instructor's campus, and you notice somebody's left their computer unlocked and they have let's say maybe they have a MySQL terminal sitting there on their desktop, and you go in there and you find the passwords table and start writing them down or something. Social engineering is another very common form of stealing information, and it's not even a technical attack. You don't have to know SQL to do it. You just have to be deceptive. So social engineering is just convincing people to give you information that they are not supposed to give you. So let's say you call somebody up and you say, hello, I'm from the IT department and I need your database password. And you're the database administrator, and you're reluctant at first, as you should be. And then the attacker says, starts kind of pressuring you into doing it. Like, fine, I'll just go, get it from someone else and tell the CEO you're not cooperating. And they'll use personal information that they can find about you on Google or something like that. They'll say, I'll go tell Sally, your manager. And you're like, oh, they know my manager's name. This must be legit. And people, unfortunately, are susceptible to this kind of attack, and they give out passwords to attackers. So the unfortunate reality is tables get stolen. You have to assume that your database tables will be stolen. That's the only safe assumption. So under that assumption, you change what you store in the database. So assume tables get stolen. Most tables are harmless. Like, let's say they steal the checked out table from the library database. Big deal. It's maybe a privacy issue, like people can know what books you have checked out. But more importantly, what if they stole your password? And maybe you're thinking even that's not really a big deal. Like, who cares if they can log into my library account? But unfortunately, a lot of people use the same password for everything, or for at least a lot of things. So if they steal your library password, then they also have your Gmail password or your Canvas password or whatever. If they gain access to your Gmail password, then a lot of accounts use email addresses for authentication purposes, and they can go and just do a password reset on all of your other accounts. And if they have access to your Gmail account, then you're in a lot of trouble. So the safest option, since we have to assume that database tables are going to be stolen, is don't store passwords in the database anywhere, ever. So nobody actually knows your password, not even the server, and not even the database administrator, not even the CEO of the company. Even if Mark Zuckerberg wanted to, he could not look up your Facebook password. Then this might sound odd to you. Then how in the world does the server know that you have logged in successfully if the server doesn't even know your password? Right? So it's essentially, its job is, when you're logging in, is, did you type in the right password? How could it possibly determine that if it doesn't know your password? Well, it has to at least store enough information to, it has to store some information about your password. So here's how it works. You type in, you take in the plain text password, you put it through some scrambler function, and I'm just kind of putting it as just a mysterious box for now. Password goes in, and out comes some scrambled string. It looks like random nonsense. It's not random, but it's just some hex string. And then you actually store the hex string in the database instead of storing the password. Okay, then so let's say this is account creation time. You put in the initial password, scramble it, save the scrambled version. Now at login time, how do we verify that they have typed in the correct password? What we do is we take in the password that they type in at login time, put it through the same scrambler, get the hash out, and compare it to the hash that was saved in the database. So that means whatever this scrambler function is, it has to be consistent. It cannot be like random. It can't be based on time. It has to always produce the same scrambled result given the same input. Okay, now how does this help us? Well, if the database is stolen, now all they get is these scrambled strings. They don't get actual passwords. But isn't that maybe still a problem? Turns out yes, but it's not directly a problem, not yet. We will see why it becomes a problem. So if they steal your hashed string, can't they somehow use that to log in? So maybe they like put that back through some scrambler, or maybe you try to put it through a descrambler or something and try to get your actual password back out. No, if you try to type this into the web server as the password, it's just going to scramble that through the same scrambler function, which is going to produce some completely different scrambled string. And that will not match what was stored in the database. So stealing the scrambled password actually doesn't help, because this is a one-way scrambler. There's no way to unscramble it. And if you put it back through the login system, it's just going to re-scramble it even further, and it won't match the right password. So this is just the scrambler is just a hash function. Well, it's more than a hash function, but at the most basic level, it is a hash function. So the hash function always has to produce the same result given the same input. It should be anyway, unlikely to produce collisions. A good one is unlikely to produce collisions. And a good one also produces a very wide range of hashes, given a more limited range of inputs. So the range of inputs is passwords that people might pick, and the range of outputs is very, very large, like 64 hexadecimal digits. More specifically, though, we use a cryptographic hash function. So this is just a hash function with more features specifically for the purposes of security. So a cryptographic hash function, first of all, is a hash function. But additionally, it should be very difficult to find an input that creates a known hash value. So if somebody does steal your table of hashed passwords, it's useless. It's almost impossible to try to guess any password that would produce that hashed string. And it has to produce a fixed length hash string. So even if I type in my password as just one character, like A or something, it's still going to produce a, say, 64-digit hex digit string as the result. Okay, so let's look at an example. Let's suppose that the hash function we're trying to use is, we just set every other bit to 0. So the goal is take some known value and scramble it. So setting every other bit to 0 would certainly scramble it. Instead of strings, my example here, I'm just going to use a simple little number. So let's say 158 is my password. This would easily work on strings too. Strings are just bits. So if my password is 158, if I scramble that with this hash function, setting every other bit to 0, then I get 136, if I were to convert that back from binary to decimal. Okay. Is this consistent? Meaning, if I put 158 into this function again, will I get 136 out? And yes, obviously. There's no randomness. It's not based on time. It's always going to produce the same output given the same input. Okay, so that's good. Is it reversible? So if I know the hash is 136, can I reverse engineer, or can I guess what the original password was? Well, we can start. So I know that if you know what the hash function is doing, I know that it's setting every other bit to 0. So that means I know that the original password at least has a 1, a 0, a 1, and a 0 in the first, third, fifth, and seventh bits. Okay, but I don't actually know what is in all of those other bits, because just because I have zeros down here in the hash doesn't mean that the original password had zeros, because that's what this hash function does, is it just turns every other bit into 0, regardless of whether it was a 1 or a 0. So no, it is not reversible. But I can start making guesses now. I know like some of this password. I know every other bit of this password. So I've narrowed down the possibilities quite a bit, and I can start making guesses for what these question marks are. So maybe I happen to guess right and get the 158, which is the actual password. But here's another interesting phenomenon is, what if I just guess like incorrectly? What if I just guess that those missing bits were all 1s? Which would mean the original password, my guess for the original password is 221, which is wrong. It's not the right password. But would the system let me log in? If the actual password was 158, so the stored hash is 136, if I type in 221 as my password, will it let me in? And the answer is yes, because 221 and 158, given this hash function, will both produce the same result. And the web server doesn't know that. It doesn't know that I typed in the wrong password. All it knows is that I typed in something that hashes to the same saved hash that I have on file. And in fact, there is no way to know that it is the wrong password. So this is a really bad cryptographic hash function, because although I can't actually prove what the original password was, I can easily reproduce some string that hashes to the same value, or in other words, that produces a collision in the hash function. All I have to do is know something about how the hash function works, and then I can easily produce some password that will let me log in. So a good cryptographic hash function, just kind of recapping what it should do, is it should be very difficult to find any string that produces a known hash. So even if you do know the hash, which you shouldn't, ideally they wouldn't, but if they stole the hashes, it should still be difficult or nearly impossible to produce a string that produces that hash. And collisions should be very, very unlikely, even for similar passwords. So if my password was AAA, and if I typed in AAB, a similar string, those two strings should produce wildly different hash functions, or hash values. So even with a good cryptographic hash function, aren't collisions still possible? So the number of possible passwords is essentially infinite. Not really. There are some limits on password length and things like that, but we can think of it for these purposes as there are an infinite number of possible passwords that somebody might choose. But there are a finite number of hash values. If the hash value has to have a fixed length, such as 64 hex digits, then some passwords are inevitably going to, or some strings are inevitably going to produce collisions in that hash function. So yes, it is possible that you could type in some random string when trying to log in to Facebook, and it might actually let you log in, even if it's not your password, if you happen to find a collision. However, it's so extremely unlikely, given the size of the number of hash values, that it's not an impractical attack, and we just kind of don't really even worry about it, other than making the hash values very large. That's essentially all you have to do. So luckily, we don't have to come up with our own hash function, and we're not really going to study it in this class. That would be like a security or cryptography class. There are lots of people who have studied this and figured out really good cryptographic hash functions. You may have heard of some of these. MD5 was popular for a long time, and then people discovered vulnerabilities in it. So hopefully it's not used anymore, has been phased out. These versions of SHA, some are older than others, or there are arguments as to whether they should still be used or not. But the point is, we don't really need to worry about that. We can just use one that is widely accepted as a good hash function. So in C#, to use one of these existing good cryptographic hash functions, there are built-in libraries. So we just can use this library if we have the right reference, DLL referenced, and then just put our password into this SHA1.computeHash function, and that'll produce the hash version of any string. Or in SQL, it also supports this function. So I can do insert into some table, and then hash any value before putting it into the column. And the type of the column is just text, because the output of SHA-1 is essentially just a hexadecimal string.